All right, in this video we're going to do a sketch of another rational function. 4x squared minus 11x plus 6 all over x minus 3. Let's go through our steps. Our first step will be domain. How do you find the domain of a rational function? You set the denominator equal to 0. Whatever you get, you don't want. Here we don't want x to be 3 because it would cause division by 0. Now let's talk about symmetry. Remember, to check for symmetry, we would put in negative x in for x. And then after simplification, if we got back what we started with, it's even. If we got back the negative of the original function, it's odd. Otherwise, it's neither. In this case, we're going to have neither, because we'll get 4x squared plus 11x plus 6 over negative x minus 3. It's not to say there's no symmetry for the graph, but there's no y-axis or origin symmetry. That's what we can easily check for at least. Okay, let's do some intercepts. We'll first start off with our x-intercept. To find where a function has x-intercepts, you set the function equal to 0 and solve for x. Since we have a function that's a fraction, that would mean where the numerator is equal to 0. 0. Let's factor this. Pretty sure it factors. That works. 4x minus 3, x minus 2. Phew! So we get x to be 3/4, x to be 2. Notice these are both x-intercepts because these numbers are in our domain. Remember to check that. We're going to have a y-intercept because the number 0 is in our domain. So by putting in 0 in for x, we get 6 over negative 3. Which means our y-intercept is 0, negative 2. That's nice. We have some points on our graph. All right. So that was all intermediate algebra. Not even college algebra, intermediate. Now we can do some crossover college algebra calculus stuff. Let's talk about vertical asymptotes and whole. Two ways you can do it. The college algebra method is to say, hey, 3 is not in the domain. So if we put 3 into the numerator, do we get 0? We're not going to get 0. So college algebra would say x equals 3 is a vertical asymptote. The other way to do it, the more, I guess, proper way of doing it, is to consider limits as we approach 3. Well, if we did so, upstairs, we would get, let's see, that'd be 4 times 9 minus 3 plus 6. Well, who cares? Indifferent phase. But the denominator is going to be 0, which means as we get closer and closer to 3, the function as a whole gets really, 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 really big. Possibly really, really, really small, depending on what side of 3 you're approaching. In either case, that means that x equals 3 is your vertical asymptote. Yep, that's a 3 there, not a backwards e. You're welcome. We don't have any holes. E, horizontal and oblique asymptotes. Okay, well, the thing is, if the degree of the numerator is 1 more than the denominator, then you have an oblique asymptote. To find it, what we have to do is rewrite our function. So 4x squared minus 11x plus 6 over x minus 3. If we rewrote this using synthetic division, this would be the same thing as 4x plus 1, that's what this says, plus 9 over x minus 3. Well, horizontal and oblique asymptotes occur when x gets really, really big or really, really small. So as x goes to infinity of this function, I broke it into pieces. I didn't mean to do that, but that's okay. As it goes towards infinity, this part goes to 0. This part does go to infinity, but the whole idea is as x gets really, really big, we're getting closer and closer to this line, 4x plus 1, which apparently is in red. That's okay. So as it turns out, y equals 4x plus 1 is your oblique asymptote. Notice if we went to negative infinity, we would have gotten the same result. Okay, so we have to take the first derivative. Sing the song, low d high minus high, d low, all over low squared. I'm going to leave it to you to show that the first derivative simplifies in the numerator as 4x squared minus 24x plus 27 over x minus 3 quantity squared. Be careful, make sure you distribute that negative through properly. The numerator then factors as 2x minus 3, 2x minus 9. Quantity squared. Okay. Seeing where the first derivative is 0, looking at the numerator, there would be 3 halves and 9 halves. To see where it does not exist, looking at the denominator, that would be where x is 3. But we should not expect a relative extrema at 3 because 3 is a vertical asymptote. So putting these numbers on a number line, we get 3 halves, 3, and then 9 halves. So now we just need to pick some numbers. You should be very well acquainted with picking numbers for this. So if I pick a number to the left of 3 halves, you get positive. Between 3 halves and 3, we get negative. Between 3 and 9 halves, you get negative. And after 9 halves, you get positive. So we are increasing from negative infinity to 3 halves, and then again after 9 halves. We are decreasing from from 3 halves to 3, union 3 to 9 halves. Why can't we put that as one interval? Speak up! I can't hear you. Because we have a vertical asymptote at 3. So we can't make it into one. It has to be disjoint. Since 3 halves and 9 halves are in the domain, there's a sign change there, and they are critical numbers. That means we have relative extrema. 3 halves goes from increase to decrease, so we have a relative max at 3 halves. And 9 halves goes from decrease to increase, so that means we have a relative min at 9 halves. Let's find those y values. 3 halves, put it into the function, you get 1. 9 halves gives you 25. New York City. What are you going to do? Okay. Part G. Concavity and inflection points. That's the second derivative. I'm going to use this guy here because it's a little bit easy to use. Okay, low, d high, minus high, d low, chain rule, all over low squared. Notice that's to the 4th power now. Okay. You can make your life a little bit easier by realizing that all 3 terms, 2 terms in the numerator, 1 term in the denominator, all have one factor of x minus 3, so you can cancel out that. That'll make our life a little bit easier. So that way you're just basically foiling the numerator. Upstairs, you would also be distributing a -2 through, because this part will have canceled. So I'm going to leave it to you to check that the second derivative simplifies as 18 over x minus 3 cubed. How nice. Well, the second derivative equaling 0, this doesn't happen because the numerator is never going to equal 0. The second derivative not existing, again, that's x equaling 3, but just like before, we can't expect this to be an inflection point because we have a vertical asymptote at 3. So again, we will put in some numbers. If we put in 0, we get negative. If we put in 5, for instance, we would get positive. That's great. So we are concave up. After 3, we're concave down. Before 3, but again, no inflection points because 3 is not in the domain. All right, putting everything together, we can make our graph. We previously found an x-intercept at 3/4, 2. Y-intercept at -2. Vertical asymptote at 3. Oblique asymptote at 4x plus 1. As far as the oblique asymptote, here's 1. Go up 4, 1, 2, 3, 4 over 1. That works, something like that. Now my scaling is going to be crazy off here because I'm running out of room. That's okay. Let's see, what else do we have? Okay. Oh, we have a relative max at 3/2, comma 1. About right there. Relative min at 9/2, comma 25. 1, 2, 3, 4, 5. I'm going to call this 25 because I can. I'm just that cool. Okay. And other than that, that's really all we have. So let's make our little number line with all of our critical numbers when we have that all on this page here. So we had a critical number at 3/2, 3, and 9/2. This was increasing, decreasing, decreasing, increasing. This was concave up. This was concave down. So we have this shape, this shape, this shape, this shape. So make sure you go through your points. So this piece is to the left of 3/2, which is right here. Now, to be honest, scaling is totally off. What it probably really did was it probably goes towards the asymptote, but again, bad scaling. This piece goes to the left of 3/2. We can do this one better. So proud of you. This guy here is up here. We know we're up here because we have a point up there. Again, go along your asymptote. And then this piece also goes along the oblique asymptote. Something like that. So, very messy. What are you going to do?